Okay, so if you want a good practice problem to prepare for the final, try to write down Sudoku as a linear programming problem. What type of problem is it going to be? Integer programming problem. And you can either do it as an integer programming problem or as a binary integer programming problem. Either one is fine. If you do it as an integer programming problem, you would want to think, what should my variables be? And so if you want to do it as an integer programming problem, and I am assuming at this point that Sudoku has become so prevalent that everybody knows what Sudoku is. If not, just like nod your head and check later today. What would you do if you want to do Sudoku as a binary integer programming problem? What would you choose as your variables? My daughter writes things backwards and I'm not picking up her habits. Yes?
Is it we do like 0, 1, 10, 100?
And that's the advanced way of doing it.
Oh, okay.
But if I want to do it as a binary programming problem, what would I do for Sudoku?
You have x, I, j, k.
Good. X, I, j, k. And there'll be 1 if the ij cell is a k and 0 otherwise. And if I do it like that, it's now binary. You don't have to do it as a binary integer programming problem. You can do it as just an integer programming problem. And if we want to do it as an integer programming problem, what would I do for my variables?
Just xij.
Xij. So I'm going to use the different substitute yij. And so yij will be
1 ij cells 1, 2.
Good.
Cells 2.
1 through 9 for entry in ij. 0, well actually, it has to be 1 through 9 in fact. There won't be a 0. So the question is, which is an easier thing to use? In some sense, they're equivalent. But which is going to have more variables, which is going to take a longer time to run. Depending on the problem you're using, certain techniques will be a little bit more efficient in terms of how many variables do things cost. Is it better to have fewer variables but more values?
Wait, is this then where you have the powers of 10?
So I'm going to get into that in just a moment.
Oh, okay.
So right now, this is the simple, standard way to code a Sudoku. And you need to figure out what the constraints are going to be, but xijk will be 1 if ij is a k, 0 otherwise, or yij is just going to be the value of the cell. And then you would have to put in all your different constraints. And then the problem is, the more constraints you have, the harder things are going to be. And so the question is, what is the best way to code all the different constraints? One trick that I really like is, instead of 1, 2, 9, do 10 to the first, 10 squared, 10 cubed, 10 to the 9th. This is a much better way to code Sudoku problems. And the reason is, in Sudoku, we're supposed to have the numbers 1 through 9 if we're doing the standard 9 by 9 Sudoku. If you do the shorter 4 by 4 Sudoku, or they've got some of them the 4 by 6, you can have slightly different variants. But you have a bunch of numbers, and you have to use each number once and only once in each grouping. You have the block grouping, the row grouping, the column grouping. If I choose these as my numbers instead of 1 through 9, there's only one way to get a sum. That's 1, 1, 1, 1, 1, 1, 1, 1, 1. Right? What's the only way to get a sum of this in this row if each number is one of these numbers? It's just got to be these numbers. I've got to have exactly 1, 1, 1.
Don't you need 10 to the 0?
I'm sorry?
Like you can't get
Oh.
that somehow.
I'm sorry, okay, so I want to start at 10 to the 0 and go up to 10 to the 8. Or, yes. Otherwise, I would just have a 0 at the end, yes. And of course, the question is, do I have to use powers of 10? Could I use something else?
Probably.
Probably. Could I use maybe powers of 2 and do things in binary? Is there a unique representation of a number and binary? And so, I hate having to worry and play games like this. I like to have my numbers so well separated that I'm fine and I don't have to worry about any of these issues. With these being separated by powers of 10, they're so far apart from each other, I don't have to worry about things aligning and reinforcing. Again, I should be fine with the binaries as well. You should be able to do this with powers of 2. This is just a little bit easier for me in terms of just making sure I'm really safe. This is a really nice trick. By choosing these as my variable numbers, it's a lot easier to do the constraints. Yes?
What are the relative runtimes of these three approaches?
No idea. So if you were actually going to do something like this, you would actually then want to check and see what the different runtimes are. One of the reasons this is so difficult is in different environments, the same code will run more or less efficiently sometimes than other code, depending on how the system architecture is set up. So certain languages are optimized for certain types of operations. So sometimes one program will be faster in one system than in another.
So if you have like a bajillion variables, you can't really do big O analysis. You just run them on like a baby problem to see how they perform relative.
I wouldn't say you can't do a big O analysis.
Okay.
You can still do the analysis, but sometimes the constants might be very important. Sometimes it might not be clear, exactly what those constants are, and you want to know exactly. It's not enough to know is it, going like into the fifth. I want to know what is that constant in front of into the fifth. That could be important. But for problems like this, you would often want to do small-scale versions first and try to get a sense of maybe which of these three is better.
Would a computer scientist know more about the runtimes explicitly for these and be able to comment on them directly?
I mean, this stuff is studied, and this stuff can easily be analyzed. I didn't really want to get into too much detail in here because we don't have too much we don't have a computer science prereq. This course was almost co-listed with CS. If it had been co-listed, I would have talked more about the runtime of the various things. But in practice, you're never going to be programming this directly. You will be programming in some system that has these packages pre-installed. Now, when you're doing that, you would want to get a sense of which ones are more efficient. And so if you were really going to be doing this stuff professionally, you would start to investigate all these different things. In terms of a first course, in terms of how deep we can get, I don't really want to go into all the detail like this. If anybody is interested, I am happy to read up on this and correspond with you about the analysis of this. This is not that hard to program. I'm happy to write programs to see which of these is going to work faster. This is not that bad to actually do by brute force these three different cases, and to actually get a sense of the relative merits. Now this is in some sense leaving mathematics in terms of a rigorous proof. Just because we check a couple of cases and get some feel for how things are growing, is that a proof which one of these is better? No, but it's good indication. It's good evidence. And this is one of the differences between proofs in different disciplines. In mathematics, we would not consider a proof looking at the runtime of the Sudoku, that's 9 by 9, the Sudoku, that's 16 by 16, and using that as conclusive to say which one is better. Maybe there are some constants that only kick in as you start getting really high up. That said, we would strongly believe evidence from a couple of small data points and get a real flavor for what's going on. So if you want a really good exercise, this is a great thing to try to program how you would do something like this.
Wait, so at the middle one, can we solve the problem in that way without using the trick?
Yes, I mean,
Oh, okay. Don't they get compounded?
I'm sorry?
Wouldn't the middle...
Well, it all comes down to how many constraints you enter. So you need to have a constraint that says each number occurs once and only once. If I require instead that my sum equals 111,111,111, the only way that can happen is if I have each number once and only once. I no longer need the constraint that each row has only one 1, each row has only one 2, each row has only one 3. I can replace all those constraints with this super constraint. As an aside, how many of you know who Richard Feynman is? Do you know that he reduced all of physics to one equation?
Yes.
Okay, what's the equation?
I think it's U equals 0.
U equals 0. This is all of physics. I don't understand why it takes a couple of years for people to get the BS or PhDs in physics. So the way he defines U is F minus ma squared plus E minus mc squared plus... He basically takes every law in physics and subtracts the right-hand side from the left-hand side and squares. What's the only way a sum of squares of real numbers can equal 0? They're all 0. So he's reduced all of physics to one equation, U equals 0. I can't even write down Nobel laureate. It's not just because I can't spell it, because there's no way anybody would believe that he got the Nobel Prize for this observation. Right? This observation was to drive home the point that just because you've compactified things does not mean you've increased your understanding. And just because we've compactified things here does not mean that we've decreased the runtime. But this is a great thing to investigate. And you are at the point now where you can investigate this. And this is one of the goals of the course, is this is a pre-core 300 level course. I've got to be very careful in terms of what prerequisites I'm going to force you to have and which prerequisites I'm going to use in the class. But I know at the same time, a lot of you have far more than the minimum needed for this class. I want you to be at the point where if you're interested in something, you can go further. I want you to be aware of certain methods that exist, so that if you actually happen to be in the real world, if you're working in a financial firm and you see a problem, you go, hey, this is similar to something I saw before, let me look at Blair. And you have just some idea of what methods might be useful. So to me, there were a couple of reasons why I wanted you to read this paper. It really shows you the issues that happen when you apply what we're doing to a real world problem. You get a sense of what are the real world issues. And this is another reason why I had so many people coming in and talking to our class about what are their issues in the real world in terms of optimizing. Some of these issues are things you would not necessarily expect. Some of the issues do not stay issues if you talk to people long enough. Any Saturday Night Live fans? I used to be a fan back when it was funny. How many of you have seen the Hans and Franz commercials recently? There was an episode of Saturday Night Live where it was a clip show, and they were collecting a bunch of their best commercials over the years. And they had one of their stars talking about why they've waited so long. And they said, we didn't want to do this show for many years because of the artistic merit and blah, 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 blah. And then we saw how successful other shows were and how much money these clip shows were producing and how little work it was. And we started finding out how much money we'd be getting and how quickly we'd be getting that money. And we decided we were being a bunch of holier-than-thou snobs and we should give the public what it wants and do a clip show and take the money. Certain issues evaporate when enough money is on the line. And so if you ask people, how much is this worth to you? In a dream world, you would have all these great things, yes. And now if you have finite resources and you have to make choices, you've got 2 hours to design the movie schedule. What are you willing to accept in 2 hours? You want to have a movie start every 20 minutes, that's great, but that could cost you. And maybe every now and then we have a gap of 25 or 30 minutes. And so this goes from having the hard constraints to having the soft constraints. Soft constraints can be violated. There's just a penalty. If you violate them too much, it's a huge penalty, and then your company will take a hit. If people consistently show up and they find the movie theater is closed, they get frustrated. This is one of the reasons why businesses often stay open when they don't have enough customers coming in to justify the cost of being open. Because they want people to be aware that they can come in. For some of these 24-hour convenience stores, how much money do you think they're getting in some of those late hours? Do you think they're paying enough for the electricity and the staff time? Do you think they're doing enough in sales? So think about it. Think of these 24-hour convenience stores. Do you think they are generating enough revenue in those hours to justify being open for those hours? No. Why will they do it?
Well, you never have people wondering if the place is open, so they might get that back in like other hours of town.
So you might get that back in other hours. This store is always there for me when I need them. I will vote with my feet and I will come back to the store.
But given that a lot of the costs for restaurants and stores are just sort of in the property rental rates, and utilities are rather small,
Yes.
I think it would seem as though, for example, the 24-hour convenience store, it would seem as though they make more money in those late hours, because otherwise it seems like you would just have repeat customers for those late hours, because in the middle of the day.
I think you can easily find. Now you also have some cost of opening and closing the store. I think you can probably, for a lot of these stores in a lot of locations, probably kill maybe 2 or 3 hours in the night and not decrease revenue. But you also would have the cost of actually closing down the store. Well, if I've got somebody in the store, they can be closing it down while they're working. But the goodwill you generate, you often do things because it generates the goodwill. So in the movie paper, a lot of the constraints we have, these were managerial constraints. We didn't need them, the manager wanted them. And so we programmed these as soft constraints. And so these are things that are desirable. And then there was a penalty function. And the more of these penalties we had, the more of a hit we got at the objective function. Another thing which we're not going to get into the class, but if you're interested, I'm happy to share a paper that my students wrote last time I taught this as a senior seminar, is what happens when you do not know parameters for your model. So again, in the movie theater paper, we assume we know what the demand is for each movie at each time of day. This is a huge assumption. So we have some kind of model, we do some kind of regression to figure out what the demand should be. So what kind of demand model were we getting in the movie paper? How is the demand for a movie over time?
Oh, it decreases over time.
Right, how does it decrease?
Exponentially.
Exponentially. All right. Almost all movies decrease exponentially over time. You know, more and more people normally do not want to go see the movie. There's a few exceptions. These are the sleepers that start off slow, word of mouth spreads. The one I always use is the Blair Project. How many of you have seen that? It was big a long time ago. And it was, you know, one of these small movies that just started out, and it was a really good word of mouth campaign. Most movies are not like that. And you have a bunch of parameters that you need to estimate. And so in terms of trying to figure out what is the demand as a function of time of day, we have to figure out what are these different parameters, and then we plug this in and we have some kind of model. This is where statistics comes in. So if you want to do, you know, something in this area, this is a wonderful operations research. It hits mathematics, it hits statistics, it hits computer science. You need to figure out what should the parameters be from your model. Well, you have a huge data set of movies, and you can often see what is the demand for the different movies. Now, if you looked at the paper, there were some parameters that you had in this paper that you would not directly have in an American market. Can anybody give me one parameter that we would not directly have in the American market?
Whether it's a Dutch holiday?
Whether it's a Dutch holiday. We might have whether or not it's an American holiday, but we will not have if it's a Dutch holiday.
Whether the Dutch soccer team is playing.
Whether or not the Dutch soccer team is playing. Do we care if the American soccer team is playing? What if we use, instead of soccer, what if we use the word football?
Yes.
Yes. So in terms of, you know, is there a big sporting event? Is there something going on that will drive demand? We do care about that. The European soccer or the European football has a far greater impact on, I think, movie attendance than American football games. In terms of just how much the country shut down and just focus on those games. And so, you know, factoring stuff like this in, factoring in the weather, the more data you have, the better model you can have. And the more data you have, the more chance you have of seeing all these different interactions. So you need really rich data sets. And these are often very hard to get. You know, you need companies that are willing to share the data with you. But from an internal perspective, if you're the company, you want a sense of, well, which data do I need to gather? Sometimes you don't know ahead of time, so just gather all the data. It's sometimes so cheap that once you're getting it, just store a couple of extra things. You don't necessarily know what you're going to need ahead of time, and if you have this stuff, you have it for later. Some of you have done surveys. Once you do a survey, it's very hard to go back and ask the people another survey question. So you sometimes ask people a little bit more than you need, just in case it comes out later that you need some more information, you want it already to be there. The other thing is, before you do a big expensive survey, what should you do? A small, less invasive survey. You want to just ask a small number of people. You want to try to find out, are there any major mistakes? Are there any major flaws? You want to do a preliminary data analysis. Is there anything that I all of a sudden realize, oh crap, I need this? And so these are really good techniques to get into. Some of the psych classes here, I think, actually go through a little bit of, you know, how you would design experiments and studies like this. Okay. So this is the class before Thanksgiving. You know, attendance is often, you know, tough in something like this. And so what I thought we would do is, you know, my plan was to talk about something that was worthy of a Nobel Prize. And while I do have a degree in physics and I could talk about finding path integrals and a lot of his ideas, this is not the appropriate environment for something like that. So I thought instead I would talk about a Nobel Prize in economics. We've already seen, in some sense, almost enough mathematics to merit 1 Nobel Prize in economics. Anybody know which Nobel Prize? Nash equilibrium. So basically what Nash needed for his equilibrium is very close to the fixed point theorems we were doing. With a little bit more work, you can read exactly which fixed point theorems Nash needed, how he needed to apply them. His Princeton thesis is very readable. It's, well, okay. By very readable, I don't mean how it's formatted. You know, the font settings back then are not the same as now. There was no tech back then. This was on typewriter, with I believe parts of it handwritten because of the math symbols. But it's on the order of 20 pages. Double space, bibliography, introductory page and whatnot. It's not a long thesis. And the mathematics behind it is, I don't believe he's proving the fixed point theorem. I believe he's applying the fixed point theorem he needs in the situation he wants. That was the clever idea. And frequently, this is where you are made or broken, is can you figure out how to use tools that are out there in clever ways that other people haven't seen? And the idea of bringing in these fixed point theorems is great. So what I want to do is I want to talk about Gale-Shapley. So how many of you have seen this in an econ or a CS class? 2 hands. Was it econ or CS? Comp sci?
Comp sci, I don't remember what it is anymore.
Okay, do you remember what it is?
Yeah, my final project on it.
Oh, excellent. And I'm glad you do remember. So this is another paper that won a Nobel Prize in economics. This was a paper in a math publication. And in fact, it was not one of the premier research journals, it was one of the more expository journals. And this is related to a problem I gave you for homework earlier in the semester. But we're going to do it not with linear programming, we're going to do it another way. We don't have to solve everything with linear programming. Linear programming is a powerful tool. Right? If I have something where I have linear constraints, and I have, you know, real variables, or maybe that are non-negative, and I have a linear objective function, linear programming is wonderful. What method do we have to solve problems like that? Simplex method. If the objective function is quadratic, we can actually still use a modification of the simplex method and we're fine. We sadly can't do quadratic polynomials in the constraints. Alright. If it's binary or integer valued, we also have issues. We don't have good ways to solve that. This leads to a whole class of complexity problems in CS. There are other techniques to solve problems. And so the problem I'm talking about is the medical school problem, medical matching. You have a bunch of schools, or if you want a bunch of hospitals, and you have a bunch of doctors, and you want to figure out how to assign them. And now in a problem like this, you have to decide which perspective are you taking? Who do you work for? And the answer is?
Hospitals.
Who pays you? Right? Where's your money coming from? When you have 2 competing influences, you can make things better for the students, you can make things better for the hospitals. Or you could try to balance the 2 and have some kind of multi-objective function. And maybe weight them equally, or maybe weight them a little bit unequally. You know, which do you think is more important, the students or the hospital? I might say maybe the hospitals, when you start to think about, you know, all the people that are being served by the doctors, maybe it's more important to have the hospitals matched appropriately than to have the students. You know, yes, you really want to work in that Hawaii hospital, we need your. So you've got very important issues to decide as to what you want to maximize. So the main problem is it's an assignment problem. How do you assign people to hospitals? I'm going to give the classic formulation of this in terms of marriage. And this is the classic formulation. So I am not going to get into modern day variants of this. I trust this is Williams and you can discuss the modern day variants. I will go with the classic problem. We have n men, 1, 2, n, and we have n women, 1, 2, n. And we want to match in pairs male, female. If you want a non-standard version, think of this as n people from Williams, and then people from Amherst who need tutoring, and you want to make sure each person from Amherst is paired with somebody from Williams who can tutor them and help get them through college. Okay, so if you want the non-traditional phrasing, you can do something like that. We need some way to do the matching. I got an idea. 1 goes with 1, 2 goes with 2, 3 goes with 3, and goes with n. Done. Problem solved. Let's go to Thanksgiving. What's wrong with this? Yes?
You don't take preferences into account?
No, but it's fast.
Yeah. It's a feasible
It
solution.
is a feasible solution. So we probably want to take into account some preferences. The other thing is, let's say people are aware of the matchings. People might have a tendency to switch. And maybe you can say, I match with somebody I don't want, you're matched with somebody you don't want, we prefer ourselves. Let's screw the people we're matched with, not you. Let's get together. In a situation like that, there would be an unstable matching, the initial configuration, because there would be an incentive for 2 people on their own to realign. So the goal is to find something stable. So goal, stability. Well, if we don't have something that's stable, what do you think would happen? Yes?
It would move into a more stable configuration over time.
Hopefully.
Hopefully.
Yeah, maybe you could get into some kind of vicious cycle. So it's not necessarily clear that you would reach an optimum, or that you would reach an equilibrium. So we want to have some kind of stability, and we want to try to maximize happiness. This is a somewhat vague term here. So what I'm doing right now is, this is a problem that I thought about giving you on part 2 of the final, in terms of doing something like this. So this is a nice way to review and see the types of problems I could ask. Okay? What kind of data do you think you want from the manual? Rankings. Ask men for rankings of women. What kind of data do you want from the women? Yes. And so what we'll do is we want to try to maximize maybe total ranking. That might be hard. Maybe what we'll do is the first goal is to just go for something that's stable. And so in a situation that's stable, no one can unilaterally team up with somebody else and switch. You might be able to do a switch with like a 3-way trade, but there'll be no 2 pairs where 2 people can say, we'll screw our partners and get together.
Can stability also mean that 2 who are together can't switch and make themselves both better off?
Well, if you're going to switch, you would need somebody to agree to switch with you.
I mean, like, you can define stability such that you are switching, like, one partner, so I'm going to go somewhere else, but
Right.
my current partner is worse off. But you also define stability such that my current partner and myself are both better off by no longer being together. Make sense?
But if you do that, so you're both better off.
Then you would have like a mutually, then you just have like a dead wrong pairing.
You would need other people to then agree to that. Now, what could happen is that maybe you and I are partners, and then we find that, this was not a good idea, we'll split off, and we need somebody who will then take us and do the trade. So I would say right now we just want a situation, a very general case, where people cannot unilaterally improve by coming to terms with each other and screwing their partners. There's a whole slew of different things you can do. I'm trying to do the simplest example right now. So we want an algorithm to come up with a stable assignment. What do we want this algorithm, what kind of properties do we want it to have? So we want it to be stable, what else do we want?
Terminates in a finite amount of time.
Terminates in a finite amount of time, and what else? Kind of given it away by using the word algorithm.
You want it to be constructive and actually.
I want it to be constructive. It's not enough to tell everybody there is a way to marry everybody off. There is a way to assign people to hospitals. There is a way to pass this course. You want a constructive method to stuff like this, right? So we want, in addition to all of this stuff, we want fast, and we want constructive. When we try and do this with linear programming, is it fast or not fast? Not fast. Why is it not fast? It's binary. We don't know how to do binary integer programming well. So over here, here's the algorithm. Do you want to take the point of view of maximizing happiness for men or for women?
Women.
Good. Somebody spoke up first. So adopt the view of maximizing women's happiness.
You should just add men and women and take a sound and maximize both.
The algorithm I'm going to do actually is primarily focused on maximizing one person, one group, or at least getting a stable matching for one group. It becomes a fascinating question to ask, how many different stable matchings do you have? And of the stable matchings, which one is optimal? So right now, I'm not necessarily finding something that's optimal. Right now, I'm concentrating on finding something that is stable, so that there's no incentive for unilateral motion. So two people can't just get together and say, we're going to agree to dump our partners and be together, which would then force our dumped partners to get together. Any music fans? There's sometimes over years when you have groups and people are dumped from the groups, sometimes the dumped group members form their own group, and the other people, get together. You can have a situation like that, right? We want to avoid a situation like that. We want a fast constructive algorithm. So here's how it works. Step one, each unmatched man proposes to the highest ranked woman. Right? So each man looks and surveys the field and goes to the woman they desire the most and says, will you marry me? And you know what the woman says? No, she doesn't say no. What does the woman say?
Yes. She says yes to her highest ranked man, the one who asks.
No. Because if she says yes, marriage is forever, marriage is eternal. What does she say?
Maybe.
She says maybe. She says, I'll consider it, stand over here, please. And she puts them in a nice little box. Well, do you think she's going to say maybe to everybody?
Some of you does.
So if she's asked by more than one man, what will she do?
She said no.
She says no to everybody except her highest ranked proposal. So each woman says maybe to their top proposer, no to the rest. In an extreme case, what could happen?
The men could all ask the same
The men could all ask the same woman. She was a math major from Williams College, highly desirable. Every man asks her to marry. What would be the best case for us?
Pick someone different.
Every man chooses somebody else. Okay? And in fact, from the point of view of the men, what do you think they should do? If this is the algorithm we're using.
Collaborate.
Collaborate and collude. So if you've ever watched the movie A Beautiful Mind,
Yeah.
there's a wonderful scene about this where John Nash is in a bar with a bunch of grad students. You do need some alcohol to survive grad school. It is a requirement. And he's coming up with the strategy as to how they should pursue women to maximize their happiness and not the woman's happiness. This is not exactly how he developed Nash equilibrium. There's some artistic licenses going on. But there's an incentive to collude. If you know the structure that's being used, you can use that to your advantage. We will assume, of course, that these are honorable men, and they will act on their true feelings. So the women each say maybe to their top proposer, no to rest. All rejected men return to the pile. So step one, step two. Now what lather, rinse, repeat. Not good today with chocolate. Okay. We keep playing the game. Now all the men who are unattached ask women to marry them again. Is it possible they might ask a woman who already has a suitor? Yes. And what will that woman do?
If he's higher than her.
If he's higher than the best she has, say, you know what, on second thought, I've decided you're not a maybe, you're a no, thank you, go back to the queue.
Doesn't this, if you do it with the men proposing, then it maximizes the men's happiness, like in the, I mean.
The men's happiness?
Yeah, because they get the top woman who will accept them, who isn't proposed to someone, by someone higher.
Wait, are you sure the men will get the top?
Yeah.
Because, right, because they'll
No,
go
'cause-
down their list. Like, there could be a woman who gets her last ranked man just because he's the only one who proposes to her, where in the other way,
This is like the traditional formulation of the problem in which the men win.
yeah.
So the men
Whoever
proposing.
whoever proposes wins,
Was it
because they
whoever
get the
proposes
highest,
wins?
because they get the highest ranked person who will accept them, while the women just get their highest ranked person who happens to propose to them.
They get the, at first they get the highest ranked person, but then if lower, you know, a man like
Right.
asks the woman if
No, but they
first
still
choice,
get-
then she can say no to the person she then maybe to.
But a man gets to go through every single woman, and if she will take him, he, like,
Yeah,
gets.
this definitely.
Just think about it, if all the men have different preferences,
right,
like if their hot first women in their ranking is different,
right.
then the men will all get their first
Okay.
rankings.
Right, so like a man only moves down if
Okay,
like,
so,
he
okay.
could never be matched
So we
with
should
that
swap
woman.
them.
who did.
Okay. I may be off by a minus sign. I could easily be off by a minus sign like this, and it may be just an instinctive bias I have as a member of the male community that I have accidentally maximized male happiness. If so, I do apologize to the women, and men, you owe me. So for something like this, one group will be very happy. One group will be less happy, but it will be stable. And so you can go through the argument and see that you will not be able to find two pairs that will switch. So we only have 2 minutes left. I'm not going to go through the analysis of why no one will switch. You can try to imagine two different pairs and what it means. But as soon as, at the end of the day, we have men and women. Every man has to be paired. What principle is lurking in the background? Pigeonhole. Pigeonhole principle. The pigeonhole principle is looking in the background that everyone is going to be matched up. Now, worst case scenario, how long could the algorithm take?
Forever.
What's the runtime?
And
So runtime will be less than equal to n squared. Yes?
Couldn't it take forever if the men never change their choices and they are lower ranked?
Well, here's the thing. In step one, how many people, worst case scenario, what's the worst case scenario for step one?
right, I mean, like, the worst case is that each of the N men has to ask all of the N women. And
So
that's-
worst case,
that's that.
we have n people asking the same woman in step one. And then, this is woman one's dream. Every man has asked her to marry him. She looks at all of them. This is the bachelor, or the bachelorette, I guess, in just one moment. She chooses whom she wants, takes that person, and then she's done. She got her top pick. Now we have n-1 women and n-1 men. By induction, we know what's going to happen. We can just keep playing the game. Worst case scenario, n-1 men all ask the same women. The more distributed they are, the better. And so, worst case, this is the runtime. And now we actually analyzed this before. This is n plus 1 over 2. So this is on the order of n squared. Or if you want n squared over 2. We also talked about how to estimate this. We could say, look at the halfway point n over 2. We have at least n over 2 terms that are at least n over 2. Have to maybe be a little bit careful with the floor function. But we can easily get a lower bound. We can easily get an upper bound. What would be an upper bound for this? N squared. So this would be less than equal to n squared, and should be greater than equal to maybe the floor of n halves times n halves. Have to be a little bit careful with that, because I want to get something just involving n, not involving n squared. So an algorithm like this is not that hard to analyze. So in terms of what goes on here, this is a very fast algorithm. It creates a situation where you have stability, but not necessarily optimality. And so then the next stage would be how we can go further with this. All right, have a great Thanksgiving.